So hello everyone. In this chapter 6 of the book, we are going to talk about viscous flow in ducts and pipes. This is part 1 of this chapter. So the acknowledgement slide as usual. This is from the fluid mechanics book, Frank White, our textbook, and some of the slides have been prepared by a colleague, Professor Barami. So I wanted to acknowledge that. So as I said, in this chapter we will talk about flow in viscous ducts. So basically we would like to study the viscous flow in ducts with various velocities, fluids, and duct shapes. So what's the range of the velocity? What is the Reynolds number? Whether the duct is a pipe, is it round or it has different shapes? It's rectangular. Is it for air? Is it for water, for oil, gas, and so on? So the basic problem is as follows. So given the pipe geometry and its added components, as you see in this picture on the left side, so this is for instance, so what you see here, so this is like a part of a refinery, like an oil refinery or a similar chemical plant. So the pump geometry and its components, such as the bands, uh, different kind of connections, diffusers, valves, fittings, and so on are given, plus the desired flow rate. So what should be the flow rate and fluid properties, and based on that, what is the pressure drop needed to drive the flow, for instance, in this pipeline. This is a very complex one. Of course, we are not going to study this in this course. Usually computer packages are used for design and analysis of such complex networks of pipes. However, it is important to know what is in the background of these codes, and what is the basic equations used to design like a pipe flow or duct flow. And this is on the right side. Here you see air ducts, for instance, used in heating, ventilation, and air conditioning. So similar principles. Here the cross section of this ducts is not round and the fluid is air. Instead of a pump, here a fan is used or a blower. So, but the principles are pretty much the same. So when we finish this chapter, you will actually you should have like the understanding and skills and some knowledge about how to design such systems, at least not a very complex network, but like at least on a straight uh, pipe or a pipe with multiple bends, and also with a pump, and you should be able to calculate the friction loss and the pressure drop in the pipe and so on. So let's go back a little bit as a refresher. So we had in previous chapter the definition of Reynolds number. Reynolds number is in fluid mechanics is the most important non-dimensional number. It is density, velocity, a characteristic length. For a pipe, the characteristic length is the diameter, usually the diameter, not the length. So if we show it as Reynolds D, then it means that this L is equal to D. So density, velocity of the fluid, characteristic length, diameter divided by the viscosity of the fluid. So it is the ratio, it's interpreted as the ratio of momentum or inertia of the fluid over the viscous forces. So it means that the larger the Reynolds number, the smaller, for instance, the viscosity. So if the Reynolds number is large, then the ratio of momentum over viscous forces is more important. So viscous forces become like less and less significant with an increase in the Reynolds number. This is what it means. So if you look at this diagram here, on the left side we do have a laminar flow. This is like velocity fluctuations versus time. So the velocity does not fluctuate, so it's a laminar flow. So small natural disturbances, even if happen, they damp quickly. If it is very small disturbance, for instance, if you have a laminar flow, you disturb it, it will damp quickly, it will not grow. Then as for instance, the velocity and Reynolds number increases, then we do see some intermittent bursts of turbulence. So these disturbances appear, disappear, they are there, they are not there. That's called, it is called like a transition from laminar to fully turbulent. So in the continuous turbulent flow, there is significant and noticeable fluctuations in the velocity components as the fluid flows in the pipe or duct. So therefore we do have a region of laminar flow, transition or intermittent flow, and fully turbulent flow. In the previous chapter, we briefly discussed the fluid in a pipe, and we said that if Reynolds number based on the diameter of the pipe is less than 2100, then the flow is laminar. If it's larger than 4000, it is fully turbulent. And as a like borderline, usually a Reynolds number of 2300 is considered as the borderline between laminar and then turbulent, because usually there it is difficult to come up with or develop equations for the transition region. As a result, for practical purposes, the flow is either considered as laminar or turbulent. So in this example, we want to see what is the range of the velocities to have laminar flow and turbulent flow, or in other words, how high the velocity could be before it becomes like turbulent. So the accepted transition Reynolds number for flow in a circular pipe is 2300. For flow through a 5 centimeter diameter pipe, at what velocity will this occur at 20 degrees C? So properties evaluated at 20 degrees C, density and viscosity. The tube diameter is given, and we want to see at what velocity transition from laminar to turbulent occurs, A for airflow and B for water flow. Okay, so we use the definition of Reynolds number and put it equal to 2300. Case A for air, the density of air, velocity unknown, diameter 5 centimeter, viscosity of air. It turns out that the velocity is 0.7 meter per second for air. So for similar thing for water, if we substitute the properties of water, density of water and same diameter, unknown velocity, viscosity of water, as you see, is much higher than viscosity of air. The dynamic viscosity of water is much higher than dynamic viscosity of air. So as a result, the velocity which makes the flow turbulent is very small in the case of water in a tube of 5 centimeter diameter. So 5 centimeter diameter is like 2 inches, right? So the flow is like about 5 centimeter per second. So 5 centimeter per second is like, it's a very small low velocity flow, is 5 meter per second. So it is the limit of laminar. So in real cases, so let me read through this discussion here. So these are very low velocities, so most engineering air and water pipe flows are turbulent, because in reality the velocities which are used are higher than these values here. So not laminar. So therefore laminar flow is kind of more, it's like it has more theoretical value. So we might expect laminar duct flow with more viscous fluids such as lubricating oils or glycerin. So this is for air and water, but sometimes the fluid is, if the fluid is like with different velocities, then the range of this fluid has different viscosities, then the range of this velocities obviously change. So for instance, if we use oil instead of water, if we use oil, then the viscosity becomes, let's say, 10 times larger, even 100 times larger for like some oils or glycerin. So then if the viscosity becomes larger for the same Reynolds number, the velocity can become larger, like 4 meter per second or 0.4 meter per second. So in other words, for a more viscous fluid such as oil, the flow remains laminar within a broader range of velocities. And that's something that you can imagine, because oil is more viscous, more sticky. It is harder to make it turbulent. Okay, so here on the left, you see a laminar flow. You see that it is quite laminar. So as the name suggests, laminar flow, there is no turbulence, no disturbance. And if disturbances occur, if for instance you gently hit this pipe here, you see like some vibration, but it will damp away because it's a laminar flow. A profound change in fluid behavior occurs at moderate Reynolds number. So when it becomes transition and then turbulent, the flow ceases being smooth and steady, laminar, and becomes fluctuating, turbulent. The changeover is called the transition. So what you see here on the right, it's like a transition and turbulent flow. So you see that the surface of this emergent jet is like wavy. So you see the waves and disturbances and turbulence. So this is like a turbulent flow on the right. So if you want to see the range of the Reynolds number, if you want to basically break it down to smaller ranges of Reynolds number, so for very low Reynolds numbers between 0 and 1, so it means that the momentum, the Reynolds number, what is the Reynolds number? Is the ratio of inertial forces divided by the viscous forces. So if Reynolds number is very small, it means that the viscous forces are very strong. So this is therefore a highly viscous laminar flow, which is called creeping flow, creeping motion, or Stokes flow, because it was developed by an engineer, scientist engineer, Stokes. So as we increase the Reynolds number, then between 1 and 100, it's like in a pipe, this is still laminar flow, but still there is a strong dependence on the Reynolds number. Between 100 and 1000 in a pipe, it's still laminar flow. Boundary layer theory is useful. So we will talk about boundary layer theory a little bit in this chapter, but mostly in the next chapter on external flows. So basically a boundary layer is so when we do have a fluid flow next to a solid wall, so that solid wall is called a boundary. So but very close to the boundary, the viscous effects are important. Far from the boundary, the viscous effects become less significant. So the boundary layer means the layer of fluid which is under the effect of viscosity, and it is very thin and it is close to the boundary or the walls of, for instance, the walls of the pipe. Then Reynolds number of 1000 to 10,000. So 1000 to 10,000, we know that 2100 and 4000 for laminar flow fully turbulent, these are actually in this range. So this is the transition to turbulence range. And for the Reynolds number higher than 10,000, it is definitely turbulent. Up until 10 to the 6, we call it moderate Reynolds number dependence. It is turbulent flow. The dependence of Reynolds number is moderate in terms of like the uh, like effect of the pressure drop, friction factor, and so on that we will see later. And Reynolds numbers larger than 10 to the power of 6, it is fully turbulent. I mean, it's been turbulent before. It's turbulent again, and the dependence on Reynolds number in the design conditions is negligible. So we will see these things that you see here, we will see this later when we want to calculate the friction factor and the pressure drop in a pipe. So in 1883, Osborne Reynolds, a British engineering professor, observed the transition to turbulence in a pipe flow by introducing a dye streak in the flow. So, so, so in the case of like it's a lower speed laminar flow. If you add some seed particles or like the dye, and then picture the process using like a transparent pipe, so like a glass or plexiglass or any kind of other transparent pipe, if you release a dye, you see that it will move, it will not be dispersed. Let's put it this way, it will not be dispersed. So that's the property of a laminar flow. Because laminar flow is laminar, it doesn't disperse like the dye. So the streak line will be just like a straight line. This is also like the streamline and the path line. Now, if the flow is turbulent, a limit that he observed to be 2300 between like laminar turbulent 2300, and that's the limit that we use now. Then he observed that the dye would disperse, and if you take a picture, well, this is what we actually happens. This is a schematic of the turbulent flow. But if you take a picture of this turbulent flow in B, so if you take a picture using at those times using like a flashlight, a spark photograph of this condition, then he observed the situation like what you see here. So he was able to freeze some of the branches of the flow, and the flow looked like this. So C is like turbulent as seen in the pictures, and A is laminar. All right, so a flow, either viscous or inviscid, could be internal or external. Internal flow occurs, in the case of flows in a pipe or in a duct. External flows are flows like over an object such as a sphere or a wing or aircraft and so on. So we usually define two cases, case of inviscid flow and viscous flow. So let's see what it means. And we actually have had it in chapter 4 as well, when we talked about Euler equation and Navier-Stokes equation, when we derived the full Navier-Stokes equation. So inviscid flow is a flow in which viscosity effects or friction is negligible, like flow far from the walls. So in reality, viscosity is always present, friction is always present. However, if you do have, let's say this is like a boundary, a wall, a plate, and you do have a flow next to the wall, you do have a boundary layer and a strong viscous effect. But further away from the boundary, the effect of the viscosity becomes negligible. So it's like the effect of the viscosity is not sensed, or it doesn't affect the equation. It does not create a velocity gradient. So if that's the case, the flow is called or considered as inviscid. In this case, the analysis of the problem becomes much easier, and the Euler equation is the governing equation. So basically, in what is Euler equation? If you look at the Navier-Stokes equation and drop the term which has viscosity in it, then you will actually uh, establish the Euler equation. Viscous flow. In a viscous flow, there is a strong effect of viscosity or friction in the flow, like near the walls. So in this case, the full Navier-Stokes equation governs the flow. Now, if we look at the profile of the laminar and turbulent flow in a pipe, let's see how it looks like. So first of all, in this diagram, NR is the same as Reynolds number. So in some books, Reynolds number is shown as NR, means the Reynolds number or number associated with the Reynolds number. So we know that in the case of a laminar flow, the velocity profile is parabolic. So what you see here, it is probably is a little bit stretched. This is not. This probably shows a parabolic velocity profile in a better way from previous chapter. And as the fluid becomes turbulent, because of the mixing effect, the fluid profile becomes more uniform. So therefore, in a turbulent flow, the velocity profile becomes kind of uniform, as you see here. And as the Reynolds number increases, it becomes more uniform or flat. So therefore, here is the laminar flow, and then these two are for turbulent flows under different conditions. Okay, so there is an entrance region where nearly inviscid upstream flow converges and enters the duct. So here we talked about inviscid flow and viscous flow, and that's related to the entrance region that we will talk about in the next slide in more details. Actually, in the slide after this. So we talked about internal flow, and we said that some of the other flows are external, the topic of the next chapter. So external flow has no restraining walls and is free to expand no matter how thick the viscous layers on the immersed body may become. So this is, for instance, on the right side, you see a sphere, and then very close to the surface of the sphere, we do have the boundary layer where the effect of viscosity is very strong. At the back of it, it's like circulation, it's called a wake, pressure drop, and turbulence. We will see it in the next chapter. So this is an example of an external flow. What you see here in this on the left is flow over a sphere or like a cross section of a cylinder, and it is very small, but Reynolds number increases. So at the left, the first picture, this one, Reynolds number is very small. So streamlines can be seen to be very smooth. This is like very close to a creeping flow. And from top to bottom, the Reynolds number increases. So you see that the Reynolds number increases, but it is still laminar. The Reynolds number is still small. And then on the right side, we keep increasing the Reynolds number. And then you see that at the back or downstream of the sphere, you see that circulations start to form. You do see some separations from the boundary, from the surface of the sphere. And so development of like circulations here. You also see them here. So that's the external flow that we will talk about in the next chapter. All right. So now, what is the entrance region that we talked about a little bit in the previous slides? So let's say you do have a duct or a pipe. What you see is like a pipe. And then this is the entrance on the left side. You see the entrance of the pipe. So as the fluid from upstream is coming in, it comes in like with a kind of assume that it does have a uniform velocity. This velocity profile, it comes in. So as soon as it comes in, the fluid close to the surface or close to the boundaries or walls of this tube will be influenced and will be affected. Therefore, a boundary layer forms right next to the walls. And you see this dashed line, that's the boundary layer, or that's the edge of the boundary layer. This figure is not to scale, so the boundary layer thickness is much smaller, and it takes a longer time for the boundary layers from all sides of the wall to actually merge. So after some time, you see that the boundary layers will actually merge. So there is therefore a developing region before this. Or to be more precise, it is based on this. This is where the boundary layers merge. So in the middle or in the center line of the pipe, the velocity remains uniform or remains the same as the velocity of the upstream here. And then on the surface, of course, the velocity is zero, and then it starts to grow. So we do have a velocity profile like this at the entrance. So at the center, uniform velocity, on the surface zero, and then there is a sharp or a steep gradient of velocity to connect the surface velocity to the center velocity. So once it is fully developed for the laminar flow, we know that the fluid profile becomes parabolic. So that's the parabolic flow profile. And after this point, this profile does not change anymore. So it remains unchanged because the velocity profile, if you remember, is only a function of r, the radius. So the radius measured with respect to the center line, and it is not a function of x. So it doesn't change with x. So after this point, the flow is called fully developed. So this is fully developed flow region. So and it starts once the boundary layers from all sides, well, a round tube doesn't have a side, from all points of the wall actually merge, and then they create a parabolic velocity profile. Before that, that's called the entrance region or the developing region, developing flow region or entrance region. So on the left here, we do have developing or entrance, and on the right of this line, we do have the fully developed. And the behavior of the fluid, such as the pressure drop, is different in the fully developed and in the developing region. So sometimes it is important to have an estimate of the entrance length, but oftentimes we neglect it. So we will see it in the next slides. How we want to actually calculate or estimate the length of the entrance region to see that if we do have a laminar flow, after what distance from the inlet, we can actually assume that the velocity profile is like a parabolic in the case of a laminar flow. So the entrance region can be estimated using these equations. So without going, to the details of, how to obtain it, for laminar flow, the entrance region can be found from the following empirical correlation. So this is actually empirical. It's been obtained by performing many experiments. So the ratio of the LE, the length of the entrance region, divided by the radius, divided by the diameter of the pipe, is equal to 0.06 times Reynolds number with respect to the diameter of the pipe. So that's for the laminar flow. So assuming the maximum Reynolds number for the laminar flow, like 2300, the longest, it means that if you plug in the 2300 here in this equation, then the LE becomes 138 times the diameter. Or in other words, this value will become 138. So it means that for a laminar flow, if you have a laminar flow in a pipe with a diameter 1, let's say 1 inch, 1-inch diameter tube, the first 138 inches of the pipe will be in the developing or entrance region. So this can be quite long. If your tube, if the length of your tube is actually small, so this can be quite large, and therefore the entrance region can be quite important. However, if you do have a closed circuit, or the length of your tube is very large, like it's a pipeline, then this entrance length can be negligible compared to the rest of the length of the system. Or if you have like a closed system with a pump in it, essentially, you do not have to worry about the entrance region because the flow keeps circulating. In the case of a turbulent flow, the entrance length is obtained from this equation. So L over D, well, multiple equations have been proposed. This is one popular, this one is popular. So 1.6 Reynolds to the power of 1/4. And this is good or best, or works best and most accurate for Reynolds less than 10 to the power of 7. So as I said, the entrance regions may be important in some cases, but oftentimes in fluid mechanics problems, we neglect it because of the reasons that I talked about. But if in a particular problem you do have a short tube for a particular application, open circuit short tube, fluid comes in and then goes out, then the entrance region must be taken into consideration when you want to, for instance, calculate the pressure drop, the friction factor, and so on. So what we will see in the rest of this chapter is actually for fully developed flows and not for the entrance region. For entrance region, some other equations and correlations are used. which are kind of special cases and not covered. So as an example here, so we do have a tube with given diameter, fluid is water, the length of the pipe is given 60 feet. The units are not SI units, these are English units, but we just go over the how to do the problem rather than looking at the numbers. So we do have a pipe with given diameter and length, and the flow rate is given. We want to see what fraction of this pipe is taken up by the entrance region. So we want to estimate the entrance region and see that what is the length of the entrance region compared to the entire length of the tube, which is 60 feet in this case. So first of all, in order to evaluate the length of the entrance region, we need to know whether the flow is laminar or turbulent, because for these two different flows, we do have different equations to estimate the entrance length. So first, we calculate the velocity from the flow rate. So the velocity is known. Then we calculate the Reynolds number, Reynolds in terms of diameter, Vd over nu. So this is the same as rho Vd over mu, but sometimes we, instead of writing rho and mu, we just use nu, and nu is equal to mu over rho, the kinematic viscosity. So in this case, it is 31,000, so we do have a turbulent flow. Then we go ahead and use the second equation in the previous slide. L over D is 1.6 times Reynolds to the power of 1/4, and this becomes 21. So LE, the length of the entrance region divided by the diameter, is 21. So since the diameter is known, we can go ahead and calculate the actual the actual length of the pipe divided by its diameter is obtained here as well to compare it with LE over D. So the actual length over D is 60 feet over half an inch, which is 1,440. So you see that the entrance length with respect to the diameter is 21. The total length is 1440. So the entrance length is only 1.5% of the entire length of the tube. So this 60 feet tube or pipe, so this is quite long, right? So this is a long pipe. So in this case, the entrance length is really negligible. But if your pipe length is like small, then you see that the entrance can become significant. It really depends on what type of problem you are looking at. All right, so this brings us to the end of part 1 of this chapter. Thank you for watching, and other parts will come shortly.